Hello everyone, my name is Manish Samson and I will be presenting the fabrication of a portable electrochemical sensor that can perform label-free detection of glyphosate in human urine. This research is significant due to these three reasons: widespread impact of glyphosate, purity of medium used, and portability for field testing. Glyphosate is one of the most common herbicides on the planet, used by Monsanto in the extremely popular Roundup products. The United States is responsible for nearly 19% of the world's consumption of glyphosate. The medium that's being used for detection is unprocessed, unfiltered, 100% human urine. This is incredibly important since glyphosate is ingested through various occupational sources and food residues. However, the glyphosate is poorly metabolized by the body and is excreted in the urine. The current analytical methods used for high accuracy detection of glyphosate require stringent pre-processing, specialized equipment, and a myriad of other factors. However, this portable sensor can operate accurately in a real urine medium with no pre-processing or additional equipment. The experimental process has four major steps which are visualized in the materials and methods section. The first step is the preparation of the spiked glyphosate urine samples. There are 8 doses in total, ranging from the control 0 dose to 72.9 nanograms per milliliter glyphosate concentration. Prior to the drop casting of the urine samples on the electrode surface was modified with a solution of DSP and DMSO. DSP is a thiol-based crosslinker which allows the glyphosate antibody to be linked with the gold electrode surface. After incubation, superblock was added to the electrode surface to reduce non-specific binding and increase operational efficiency. The urine solutions were drop casted on the electrode surface and incubated to allow proper adsorption onto the electrode. The glyphosate antigen in the urine samples binds with the glyphosate antibody on the electrode surface, causing a modulation in the electric signal, which was gauged through two electrochemical techniques: chronoamperometry and electrical impedance spectroscopy. The sensing platform presents us with an extraordinary opportunity to transduce chemical reactions into electrical signals for further analysis. This experimental process was done with a portable test device while using the benchtop laboratory method to confirm the accuracy of the experimental design. In figures A and B of results, we see the calibrated dose response to the increasing concentrations of glyphosate in the urine samples. These figures show a positive correlation between the average current and the glyphosate concentration in both the test device and the benchtop laboratory method. Although we know that the test device can recognize different concentrations of glyphosate with the appropriate electrical signal modulation, there are multiple facets that need to be considered when implementing the test device for practical applications in real-time environments. In order to determine the viability of the portable sensing platform, a multitude of performance metrics were compiled. In figure E, the subsequent data collected from the two testing methods were compared, and a Pearson correlation factor of 0.9943 was derived from the data. This indicates a strong correlation between the performance of the benchtop method and the portable test device. This indicates a high translational strength with the high efficacy for field deployment using the portable test device. The second performance metric used was a stability reproducibility test, which involved collecting the raw current value across 8 electrode chips. This data can be seen in figure D, which displays an average current value of 17.8 microamps with an interchip variation of 9.55%. This is below the industry standard of 10% and was done in real unprocessed human urine. The third performance metric was to determine the selectivity of the sensing platform and whether it could accurately sense glyphosate in the presence of interfering analytes. The 3 analytes used were malathion, chlorpyrifos, and 3-phenoxybenzoic acid, all of which are common pesticides and have similar molecular structures to glyphosate. The data collected from this experiment is compiled in figure C and shows a 5.8% difference in EIS response between the stock glyphosate solution and the cocktail of interfering analytes. This proves to us that even in low concentrations of glyphosate, specificity and selectivity of the portable test system is maintained. Finally, the last performance metric is a cross-validation study which compares the performance of the portable test device with a gold standard analytical method called UPLC, or Ultra Performance Liquid Chromatography, across low, mid, and high glyphosate concentrations. This data is seen in figure F, which shows that the inter-method variability was well within 10%. A p-value of greater than 0.05 indicated that the difference in the performance between the two methods was non-significant. Therefore, we can conclude that this portable test device can reliably and selectively detect glyphosate in 100% unprocessed human urine and possesses increased potential for applications in point-of-care systems and bioanalytical diagnostic equipment. The importance of this in the field of biosensing is that this technology can be modified for the detection of other analytes across a wide myriad of research sectors. I'm excited to see the permutations of this technology and what is made next. Thank you for your time.